Hello everyone. Today is December 19 and we are ready to open a new problem from LeetCode for our Coding Advent Calendar. Today's problem is about graphs. This one is easy, so let's solve it and discuss the solution. Here is a problem for today. Find if path exists in graph. There is a bidirectional graph with n vertices, where each vertex is labeled from 0 to n-1 inclusive. The edges in graph are represented in as a two-dimensional integer array edges, where each item in this array is single-dimensional array. So each value is source and destination, so it denotes to bidirectional edge between vertex u and v. Every vertex pair is connected to at most one edge, and no vertex has edge to itself. You want to determine if there is a valid path that exists from vertex source to vertex destination. Given edges and the integer n, source and destination, return true if there is a valid path from source to destination, otherwise return false. So here is first example, 0, 1, 2, and source is 0, destination is 2. So obviously there is a path and even two ways to solve this, from 0 to 2, from 0 to 1, and then to 2. Second example, in this case graph is splitted into two pieces, and source is in one piece, destination is in another piece, so there is no connection between source and destination. In this case we need to return false. How are we going to solve this problem? So since this is a find path in graph problem, I think the classical algorithm of finding path called BFS will help us here. So we will do like this. We will create a BFS function which will solve our problem and give us an answer, but we also need to send here a graph and source and destination. In our problem, graph is represented as two-dimensional arrays. Technically this is not two-dimensional array, this is array of arrays, but nevertheless it's not very comfortable data structure to work with. We will do another one. We will do this dictionary of int to list of ints, build graph, and we will send our input data structure here. So once we have this data structure, we will send it here, graph int s, int destination, and our solution should look like return BFS. Then we will build graph from edges, and we will pass source and destination. Okay, so how are we going to build graph and why this data structure should work? It should work because it will allow us to see all connections from particular edge for particular vertex to other vertices. To all vertices it is connected. From any of those vertex we can also reuse this data structure to see that vertex connections. and so on. So this is very useful data structure. It works in constant time to check, to add, and to remove. And as a value, there is a list here, and list here works for us because we need to go through all connections for particular vertex. So we will transform our edges to this dictionary. Oh, it's edges, right? Edge in edges. If dictionary does not contain edge, edge 0, we need to add this edge 0 with a new list of integers, right? And the same for h1, because this graph, this is bidirectional graph, so if 0 is connected to 1, then 1 is connected to 0. So we will reflect that here in our dictionary. And after that, we need to do this. Add information about 0 connected to 1 and 1 connected to 0. And we will return our dictionary. So our graph is completed. Now we need to use BFS. How BFS works? We take one node, it would be our source node, and we check all nodes connected to this one. Every single node we check, we need to remember, because there can be cyclic dependencies, and we need not to check any node twice. So we need to keep track of visited nodes, and hash set will help us here. Next, we will take the list of all connections from current node, and we will add them to queue. For each queue value, we will repeat the process. We will take the value, find all connections from this, and check if any of these connections is our destination. If it is, we need to return true immediately and complete our program. If it's not, we need to just keep searching until queue is empty, and then we can return false. So we need to create our queue. And we need to initialize it with our source. So while queue count is more than 0, we need to take a value n. We take this value. If n equal to d, if it's our destination, immediately return true. If not, then check X in dictionary of node of this current node. If it is already visited, then we continue and skip this X. If it's not, then we add it to visited. And in queue. So how it works: imagine our first node is connected to two nodes. We will add both nodes in queue. We will check first node and add that node next connections to queue. Then we check second node in queue, which is the second connection of our source node. And this way, layer by layer, we will check all connections from source to all other nodes. If one of those nodes is our destination, we can return true. Otherwise, we need to return false. That's it. Okay, dictionary. Our dictionary is our graph. Okay, so both cases work. Let's submit it. Okay, our solution beats almost 90% of all submitted solutions and almost 60% in terms of memory. So what is our performance of our algorithm? So first we need to build the graph, right? In order to do this, we need to go through these edges once. So it's big O of n, because these add operations are big O of 1, so they are constant time. So this process is big O of n. And here we check every node only once, because we keep track of visited nodes. So it's also big O of n. So the CPU consumption is big O of time consumption is big O of n, and memory consumption is also it is actually no, here it will not be big O of n, because we also need to check every single node. So it will be big O of n m, where m are number of connections, right? Because in worst case scenario, every single vertex is connected to every other vertex. So it is big O of nm, where n is the number of vertices, m is the number of connections. Right? Right. And the same for memory consumption, the same for memory, because we store this graph in a way that stores all connections between all vertices. So I am not sure if it's possible to solve this problem faster and better. If you can, let me know in comments how you did that. I need to correct myself. Both time and memory consumption are big O of n plus m, not big O of n multiplied by m. It is important to find mistakes in own judgments. The identification of big O notation for algorithm can be not an easy thing, and there is a special thing called master theorem just for this. Google it if you want to find out more. See you tomorrow.